The key idea is to generate accurate and plausible full-body human motion from a sparse observation that's coming from a head-mounted device.
Welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. We host early career academics and PhD students to share their cutting-edge research in computer vision, machine learning, and everything in between. I'm your host, Itzik Ben Shabbat, a researcher by day and podcaster by night. Let's get started. Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. Today we'll be talking about the paper HMD-NeMo, Online 3D Avatar Motion Generation from Sparse Observations. This paper was published in ICCV 2023, and I'm happy to host the first author of the paper, Sadegh Aliakbarian. Hello and welcome to the podcast. Can you introduce yourself?
Hi, Itzik. Sure. I'm Sadegh. I'm a researcher at Microsoft in Cambridge, UK, where I'm working on Microsoft Mesh, which our team goal is to improve the experience of virtual presence.
Nice. And who are the co-authors of the paper?
Co-authors are Fatima, David, Pashmina, and Darren, all my colleagues at Microsoft.
Right. So let's get to it. In a TLDR kind of format, what is this paper about?
Yeah, this paper is about, as I said, generating full body human motion. There are a few key features in real time, given a sparse observation, while dealing with missing observations. So, yeah.
Wait, but observations of what, right? So what is your input?
Yeah. So consider you're wearing a head-mounted device like HoloLens or Oculus Quest. What you get often is the head location and orientation, as well as the hand location and orientation. And this is the only information that we have.
Right. So basically, you're getting the head location and direction, maybe some hand locations and direction. This is your input. And from this, you're generating a full body motion kind of poses through time. Amazing. Yes. Super interesting. Okay. But what is this used for? So why is this an important problem to solve?
Yeah, that's a good question. In our team, we mostly focus on virtual presence in mixed reality scenarios. And these virtual reality or mixed reality headsets are the common device to use. And this signal that I mentioned, head and hand representation, is the only signal that you get. And with people at the heart of mixed reality applications, it's quite important to be able to generate a faithful, realistic, accurate representation of the humans in such scenarios.
And what are the main challenges here?
The main challenge is, there are a couple of challenges. One is because we're working with these devices, the models should be super lightweight that can run on edge. The other thing is that the signal that we have is for upper body, head and hands. And often in videos from different companies like Microsoft or Meta, you see that they're floating upper bodies as avatars. There's no leg, because solving for leg is super hard because there's no signal for legs. This is another challenge. So these are the main two challenges.
Right. And if you had to distill what is the key contribution of this paper, what would it be?
Yeah, the key contribution is, I guess this paper does it for the first time, that solves for partial hand observation. Often the case, almost all of the existing approaches that solve this problem rely on motion controllers, that both hands are always available. And this paper addressed the problem of the scenario where you have, for example, hand tracking. For example, in HoloLens, where the hands can go in and out of field of view. And once it's out of field of view, you lose hand tracking. So the model deals with partial hand observation.
Right. Okay. Let me just see that I got what you're saying, right? So you put your whatever head-mounted device on your head. You got its location. Now you have your, there you go. You got the HoloLens 2, right?
Yes.
So you got that device on your head. and then you got your hands coming in and out. Now, most of the time you won't have a controller, or some of the time you won't have a controller to go along with it. So basically what you're saying is we have the head all the time, but the hands can go in and can go out, so we can't always track them. And what you want to do, you want to get all of these sparse signals and generate the body motion, but the full body motion, right? Legs as well. This is super challenging and super interesting, and I can't wait to hear how you guys did it. But before we do, which one or two papers should people read before reading your paper?
Yeah. There is one paper that I really enjoyed reading, and this is quite recent, I guess. It's called Avatar Poser. This is the second best approach now, very competitive, that does solve this problem in an online fashion. It's a transformer-based approach that takes head and hand representation as input, generates full body motion. It writtens quite nicely, fun to read. And there is another group of papers that I really like, and I haven't explored that area yet, is the one that focuses on physics-based simulator to generate physically plausible lower bodies, which often are based on reinforcement learning. So those kind of approaches focus on generating physically plausible lower bodies. I like those approaches.
Cool. I'll make sure to put links to these papers in the episode's description. Okay, let's get to it. So I'm really curious. So what did you do and how did you do it?
Yeah, basically, the approach that we have is based on recurrent neural networks to learn temporal aspect of the data, and transformers to learn the spatial aspect of the data. And we have a simple yet effective module called TAMT, or Temporally Adaptable Mask Token, to deal with partial hand observation. So if I want to start from the beginning of the pipeline, it's like, let's start by telling you what is the input representation. So as I said, input representation is head and hand, location and orientation. We also additionally provide the velocity of these 3 points. What we additionally have, and this thing that I mentioned is quite common, but what we additionally have is we provide the representation of hands in the head space. So we have some sort of local representation of the pose by providing hands in the head space. So we do not need to care about where I am in the world. Wherever I am, my hands relative to my head is something like this. So this very low dimensional input representation is then passed through an MLP to come up with an embedding representation of each of these input signals. But these signals are temporally, there's no temporal information yet, and there is no correlation between each other has been explored by the model yet. So what we do is, in 2 steps, we capture both aspects. First, for each of these signals, like head, left hand, right hand, we have a GRU, a very tiny GRU, that learns how these signals temporally evolve over time. Once we have such information, then the hidden state of these GRUs are going to be the input to a transformer model. And the self-attention mechanism in transformer encoder learns how these representations are spatially correlated. Because, for example, if I'm walking forward and my right hand is swinging, it often indicates the other hand, the left hand, is also swinging in a different cycle. So it's important to learn the correlation between left hand, right hand, and the head. So to learn more about the full body.
Let me stop you there, because I feel like this is a lot to take in, and I want to do a short recap to see that I understand, right? So your input is low dimensional, right? You take the XYZ coordinates and the orientation, which is the, I guess, 9-element matrix or 6-element.
60, yeah.
Yeah, right. It's a 6 degree of freedom, right? So you have another 6 elements, so that's 9, but you also have the velocities. So it's a total of 12 elements in the input vector for each of your nodes, right? So your right hand, your left hand, your head. Is that correct?
To be exact, it is velocity of the location as well as orientation velocities or rotation velocities. So it's 9 for absolute values, 9 for velocities.
Right. So a total of 18 inputs per node, right? So we got that, but then it's not only their kind of absolute location; it's also with relation to the head, right? So it's like local coordinate frame. So you don't need to kind of take into account like these kind of global registration where you are in the room. You always know where you are with relation to the head, right? So this is your input. So you feed that into an MLP and you project it into kind of this higher dimensional space. This becomes the input to a bunch of GRUs, right? That you use to kind of get the temporal relation, right? So basically there's like two things here, right? Temporal connections and spatial connections. So you solve the temporal connections with the GRUs, right? You feed your inputs, you get like these temporal dependencies, and then you feed that into the transformer that gives you the spatial ones. So far, I got it right?
Yes, 100%.
Okay. Cool. Really interesting. What's the next part?
The next part is that the output of transformer is then passed into two decoders. One solving the pose parameters, the joint orientations of the full body, and the other one solves for the global position of the body, so the translation in the environment. So these are two decoders, both autoregressive based on GRUs, very simple. One thing we have is that in this architecture that we discussed, we assume that the hands are always given because we pass something into an MLP and then to GRU and to transformers. But as I said, in hand tracking scenarios, hands may be unobserved. So what we do is we take the output of the transformer at previous time step and come up with a representation that represents the very next time step for each of the hands. And if in the next time step, one hand is unobserved, we use the representation that's coming from the previous frame. So we temporally update a representation of the hand, the next possible hand representation. And if a hand observation is missing, we use that information.
Right. So instead of like the naive or silly or uninformative case where one hand is missing, so you put all zeros in your input, right? You don't want to do that. That's not informative. That's not the right thing. You have this part that, like, let's call it kind of like a switching mechanism, right? Where you, instead of whenever the hand is missing, you're going to use this kind of predicted representation of where the hand is probably going to be, right?
Exactly. And this is kind of makes sense because we have such a strong information about all the past information about that particular hand that is going to be missing in the next frame. Why not using that?
Right. And one of the things I found really interesting is that you kind of did an analysis of how much of the time the hands are missing in these kind of head-mounted devices. And it's like 50% of the time you're missing one of the hands, right? So that's quite often.
You lose a lot of information.
Yeah. So you need to bring it from somewhere.
Yes.
And I guess when we talk about the results a little bit, then we can discuss if the hand is missing for a long, long time, how much is a lot, right? So how much is...
Yeah.
Because it makes sense to me that for short time spans where the hand is missing, then it would be great, right? Because if you're predicting the next frame, then sure, if it's missing for a short while, you're going to be able to do a good job, right? But if it's missing for a long time, you kind of need to start being imaginative where the hand could be in a long time span. That's an interesting question. But let's talk about it in the result. Okay, let's continue with the approach.
Yeah. Basically, the method is that simple. So it's like a very straightforward network, and we have the results, and we have also an auxiliary task during training that, given the output of the transformer, we predict the joint global sixth-off for the entire body. So the decoders that we have is solving for theta parameters of SMPL, which is, except for the root, which is global orientation, it's all local rotations of different joints. This is informative, but because our input signal is global sixth-offs, we found that the auxiliary task of predicting the global sixth-off of the entire body is actually quite helpful. And that's it. That's the entire method.
Right, but how do you train this? So what is your loss?
So yeah, we have 5 loss functions that has been added together, a lot of them. So we have the reconstruction loss. The output of the model for the 2 decoders is global position and the pose parameters for the entire body. So we have a reconstruction loss for that. We have a temporal smoothness loss function that they say the velocity of changes in the generated output should be very similar to the velocity of changes in the ground truth. Then we have the loss function on top of the auxiliary task that I mentioned. And we have another loss function that is encouraging the temporally adaptable mass token, the TAMPT module, to generate features that are good to represent the future missing hand. And that is a simple forecasting loss function. I have the information from time 0 to time t-1. From that representation, I estimate the 6th of a hand at time t, and I have a loss function for that. So we encourage our TAMPT module to predict good representation. And the other loss function that we have, in addition to reconstruction loss, is we not only compute the reconstruction loss in theta space, the local joint rotation space, we compute the loss on the global joint 6/10 as well. So yeah, these are the all 5 loss functions that we have.
Yeah, this is the SE3 loss, right?
Yes.
Yeah. In your ablation study, I saw that like the boost that this one gave was really significant.
Yes. And there is a very simple answer to that one. Why is that? I can mention now if you want. Basically, if you make a mistake in your root orientation, you rotate the entire body because all of the joints are relative. And that's a small error. If you make the perfect prediction for the rest of the body, that's a small error in terms of thetas. But when you compute the global joint rotations and positions, you rotated the entire body. That's a large error. So that's loss function actually accounts for that.
Right. Yeah. Because everything is relative to like this local coordinate frame. Then if you make one small mistake there, it's all cumulative, right? Okay. Super interesting. Yeah. So what do you do at inference time?
Okay. That's a good question. One thing we can do is we train the model, we provide the input to it, and it generates a pose. And often the results are quite impressive. This is very, visually very close to the input signal you see a natural motion. But if you zoom in, you see that with almost all learning-based approaches like neural networks, the predictions are not 100% accurate. So for example, if my hand tracking observation is here, my prediction could be 2 centimeters away from it. And sometimes it's okay, as long as it's plausible. Sometimes it's not. For example, consider you want to interact with the virtual objects in a virtual environment. Being 2 centimeters away from that object is not okay. You want it to be super accurate. So what we do is that we do a few iterations of optimization on top of the prediction of the network to make sure that we optimize the parameters of the pose such that we actually meet the head and hand observations.
Right, but you mentioned that one of your kind of criteria is to be online and super quick. Yeah. How much does that impact the speed performance?
That's a good question, and optimizations are basically slow. But because HMD-NeMo predicts quite very accurate output, we found that we only need one iteration of optimization. That's enough. And that could be quite fast if you implement it efficiently in C++, for example. So it's super, super fast. Neural network inference for HMD-NeMo runs at 300 FPS on a laptop CPU. And optimization adds only a little bit on top of that.
Wow, that's super fast. Yeah. If it's one iteration, is it still called optimization? I would call it a correction state. But yeah, it's an optimization problem. But yeah, I can totally understand.
Sounds good.
Right? Because in those kind of scenario, like virtual or augmented scenarios, this very small mistake can be very visually displeasing. So that small correction is really important.
Exactly.
Okay, so let's move on to talk about the results. How do you even evaluate this kind of method?
Yeah, that's a good question. There is a common data set for that, AMAS, super big human motion capture data. There are a lot of scenarios in AMAS, which, for example, we may not be interested in virtual reality experiences like martial arts. We do not care about that much. So in this topic, there has been a trend that we use a subset of AMAS, which is mostly like normal human behavior, like walking, sitting, interacting with objects, and this kind of stuff. So often recent approaches that work on this problem report on that subset of AMAS. And we have two metrics for that. One that measures the accuracy of the poses, which we call MPJPE, or mean per joint position error. And the other one somehow measures the plausibility of the generated motion, which is MPJVE for velocity error. And we basically report these two metrics on the test set that we have.
And you have all the bold numbers. You guys are the best. The paper got accepted, of course.
Yeah.
But in which cases does the method fail?
That's a good question. Our method, as well as almost all existing approaches, fail when there is crazy lower body motion. For example, consider that I'm having my hands like this and I kick a ball with my leg. There is no observation, there is no signal that indicates that I moved my lower leg because my upper body is stationary. So all of the existing approaches basically fail in that scenario because there is no signal. This is one common failure. The other common failure is when you're walking, you may observe foot skating or foot sliding because, again, we do not have any physics feedback that says, oh, there is a friction, you do not have to slide. Or we may have ground intersection or hovering above the ground because we do not have height information or the body shape information. And these are like really hard to obtain from these 3-point tracking information. So these are the super challenging problems that one of the reviewers said, oh, how do you estimate the person's body height or body shape? We don't, it's hard. But that's a valid question. So yeah, this is a number of failure cases that we observe. One thing that I wanted to mention about experiments is that, as I mentioned, nobody addresses the problem of motion generation in hand tracking scenarios. So there were no baselines to compare with. So what we did was we compared our temporally adaptable mass tokens with simple mass tokens. Like if you use PyTorch, you can use NN params. You learn a bunch of parameters during training that represent missing observations. And at the test time, they're learned but fixed. And we compare our approach to this learned and not fixed and adaptable over time at the test time. And we show that, oh, this is massively improved the plausibility of the generated motions. The other thing about the experiments that I like is the study that we did on optimization. Consider the classical optimization scenario where, for example, your data energy term is an L2 loss function. You say, oh, this is my predicted right wrist, and this is the observation for the right wrist. This is the L2 error, minimize that during optimization. That's good if you have an observation for the right wrist. If you do not have that in hand tracking scenarios, this is quite common, 50% of the time you do not have that. What do you optimize against? If, coming back to your previous question, that if I, for a long time, I do not observe any right wrist information, my model generates and hallucinates how it should look like, generates something, and after like 100 frames, a new hand observation comes in, which is far, far away from my prediction, the hallucinated hand. So if I do optimize with a non-robust L2 energy term, there should be a huge jump because I wanted to meet that observation, and that breaks the plausibility of the model. The output is not plausible, it's jittery. You see an observation, you jump to that, and there are a lot of things going on, and we do not want to look implausible in virtual reality experiences. So what we do for that, we there is well-established studies on robust optimizations, And we use that in this scenario, that we say, if the observation is far away from the prediction, do not penalize it that much. So consider that you have an L2 loss of this shape, and you say, if the error is too far, smooth out, do not penalize too much. And that's quite effective because you slowly push toward the observation rather than quickly.
Right. This is a really interesting point that I want to take a minute to recap it, right? So basically what you're saying, if you use the standard naive L2 loss to optimize your final output, let's say wrist location, then you get something very jittery because, you had the prediction in one place and the actual wrist is in another place. So it jumps to it, right? But what you're kind of saying that instead of L2, you should use a more robust function that will treat outliers or large jumps in a better way, that it wouldn't jump. It will kind of smoothly, slowly go into that point in order to avoid this jittery effect, right?
Exactly. This is considered to be as an outlier, that we do not force it to be minimize the energy time.
Yeah. Really interesting and a nice approach to solve it with the robust optimization solution. Were there any unexpected findings?
Unexpected finding? Yeah. In AMAS, when you simulate, so one thing about how we train with head-on-hand representation on AMAS, we actually do not have any head-mounted device signal on AMAS. So we simulate a field of view of, for example, HoloLens on AMAS, and we say, oh, these are the parts that hands are visible, these are the parts that hands are not visible. And there are a lot of sequences that, for example, you walk around and looking up, so there is no hand tracking. And in those scenarios, if it's long, even if it's long, you see plausible hand motions. I was quite surprised that I can see good hallucination by the model, and it's not overfitted on the AMAS data because we tested in real data. We actually tested with actual HoloLens, or we did remove one part of the AMAS data set and train on the other to make sure that there is no overfitting. So, but I was quite surprised that we can generate quite long motion predictions with minimal observation of only the head.
Okay, but this is probably outside the scope of the paper, but can it actually run on an end device, let's say on the HoloLens 2?
Yes. We actually do that. We test on the edge devices. It's quite feasible because it runs real time on CPU.
Right, super impressive. Okay, so I guess we have the paper and results covered, and it's time to kind of talk a little bit about conclusions and future works. So how do you see the impact of the paper going forward?
Yeah, I guess along with a couple of other approaches, as I mentioned, avatar poser, there has been great progress in generating full body motion from head and hand observation. And I would love to see in practice that we do not see floating upper bodies anymore in different enterprise applications. We actually see full body motions. But I see that it's super hard because you do not want to see this implausible foot skating that I mentioned, for example. But yeah, I guess there is a huge progress in generating full body motion, and I would love to see that in practice.
Right. Any future projects, recommendations to any PhD listeners out there?
Yes, this topic is super interesting. There is a huge room for improvement. Errors are still large. The problem that I mentioned, for example, with my approach is there is no, at least I couldn't find a good way of learning the shape parameters or the height of the person. These are useful information. If someone can infer body shape, that could improve the results quite a lot. Combining it with physics-based simulator to generate physically plausible lower body is a very interesting area. I have one single problem with those approaches, that they assume that the environment is given. They assume that, for example, if I have a sofa in my room that I want to sit in while wearing my head mounted device, I need to simulate that in the physics simulator because they should be the same. And this is very impractical, but super interesting exploration can be done. For example, if someone can use a physics-based simulator and generate plausible scene or environment at the same time that predicts the pose, that's amazing. And with something like HoloLens, there is a real-time environment scanner all the time, so you can actually get some signal. So combining all of these tools that we have with, for example, HoloLens and environment scanning and physics-based simulator, learning-based approaches, there are a lot of interesting things ahead.
Wow. Yeah, we're living in the future. Okay, really interesting future directions. I can't wait to see what comes next. But this brings us to my favorite part of the podcast. What did reviewer 2 say? So please share some insightful comments the reviewers had in the review process.
Yeah, actually, I was lucky enough that reviewer 2 was super nice to me. I had good reviews, but I had like hard questions, like how do you infer the height of the subject? This is an interesting problem. For example, if the person wearing the device is short, do you infer it as sitting of a long person, or how do you deal with that? How do you deal with different shapes in your training data set? What do you do then? So these are interesting questions that we didn't have answer for. We discussed that in the paper. There were questions about, why GRUs plus transformers? Why not only transformers? Why not only GRUs? And these are good questions. And for example, here at Microsoft, we care a lot about efficiency. So we had to make design choices that are more or less super lightweight. So we had to justify that. Sometimes if I use transformer, I may get better performance. I get smaller errors, but we didn't go for that. But I would say that the question about shape estimation from 3-point tracking was an interesting one. If someone can address that, that's super interesting.
Yeah, I think this is like a very good starting point for a future work, like future project, because like I know that there's like, I don't know, this kind of heuristic or, rule of thumb that if you spread your hands all the way to the sides, it's supposed to be approximately your height or something like that. But I think it also raises a question about kind of diversity and all of these kind of how do we make sure that this thing would work for any person of any size, any shape. And while for sure this is outside the scope of this paper, right? Because this paper was about how do we take these sparse inputs and give n output, right? It's about the feasibility of this. But now that we know that we can do this, there's the question of, okay, now how can we do this that works for everyone, right? And I think it's an interesting question to answer in future work. I guess data, like appropriate data that kind of spans the population is the place to start. But I don't know, there's probably a lot of other things to do as well.
You touched on a super, super important aspect of it. Fairness, inclusiveness of the approach is super important. If someone want to ship an approach on Microsoft Mesh, it should be inclusive. It should be fair across all body shapes, all body types. It's a lot of work. It's not about like having an approach can generate a motion that looks good. It should look good for everyone.
Yeah, and I mean, I can understand like from a product viewpoint how this can be solved, right? You can input your approximate measurements, and that could be like a workaround, right? But you don't want people to start doing that. They probably won't measure, or they won't measure right? There's a lot of errors involved. You would potentially want this experience to be seamless, right? In a product scenario. But it's a very interesting future research question. Exactly.
But as you said, there are like different enrollment settings. As you said, open your arms and we can approximate your height, and you need to confirm that. We do not make a judgment before you confirm that. But yeah, there are a lot of approaches, but user studies need to be done. Which experience is better? Do I need to this, or do the user need to provide the height, or should I take a picture to infer that? Or there are a lot of things that we do not know which one is the best.
Yeah, and since you have like the tracking of the wrist, this is usually okay, right? So you can say, okay, touch your knee, touch your other knee, touch your foot, and then you can get like these kind of, starting points for all of these kind of things with your existing measuring capabilities. But yes, super interesting future. All right. So Sadegh, thank you very much for being a part of the podcast. And until next time, let your papers do the talking.
Yeah, thank you for having me.
Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.